Ready? Okay, thank you. So I thought I'd start by writing all the useful results that we have used in differentiation. Some of them, of course, will come in handy, and all of them are already in your formula booklet, but it would be nice to connect this to the rules of integration. As we know, integration is anti-differentiation. So when all these results are integrated, you're supposed to get this back plus c. Understand? So the algebraic one that we did was just x to the power n. Of course, all the differentiating term by term works for any function. So, but when you have an algebraic function, this is what works for it. For exponential, do not forget that exponential is being repeated. You know, remember they have differentiate, you have integrate story. Similarly, when you integrate the exponential function, you get the exponential function back. Exponential function, not exponential of anything else, as long as it's exponential x. Okay? Then when you have exponential f of x, this is what we do in differentiation. It means when your exponential is flagged by the derivative of what you have here, then you're supposed to get this back on integration. We'll look at that shortly. When you have a to the power x, not e now. When you have a to the power x, this is what you have. In integration, the integral of this will be there. We will write the result differently. You will see why I'm writing the result differently up there. Because I'll be writing divided by lim a for reason. Similarly, for natural log, this is what you have, which is why in general, when you integrate a derivative divided by the function, you get back the natural log of the original function. We mentioned that on Zoom on Saturday. And similarly, for logarithm of any other base, for trig functions, sine gives you cos, integral of cos gives you back sine. Cos gives you negative sine, integral of sine gives you negative cos. The minus just transfer to the other side, just like dividing both sides by negative 1. And negative 1 is a constant, so it can move in and out of the integration sign at will. Derivative of tan is sec squared, so integral of sec squared will give you back your tan. You must have seen sec squared in your worksheet already. So when you integrate sec squared, you just write tan of the function back. As long as that function is just x for now. We'll look at what happens when you have a linear function instead of x, ax plus b. That's a different worksheet that I've prepared. I think that's worksheet 3 or 4. I gave you that also. I hope I printed that. Or maybe I did not. Did I give you integral of f of ax plus b? Yeah. Aha, all right. So we'll look at that. Let's take into things one by one. So for cosec, it gives cosec and tan, cosec and cot, sorry. So when you see the product of cosec and cot in an integral sign, you take it back to cosec. If it consists of minus, of course, it's plus. But when it is plus, you know that minus must be produced on the other end. And of course, cot gives us cosec squared. Now, let's take this to integration. As a result of this table, we have the following integral. Oh, I forgot the special integrals. The derivatives of arc sine, arc cos, and arc tan. Let's write that, please. But I won't write that in 2 steps. I'll just write the ordinary function. Yes, what is the arc tan of sine? Do you remember? Derivative of arc sine of x. Yes, you remember? 1 over square roots. Yes. 1 minus x squared. What about arc cos? Negative 1 over square roots.
1 minus x.
Same thing, right? What about arc tan?
1 over.
So that's 1 over 1 plus x squared. Okay? So we must remember this. Let me put some sort of demarcation. Okay? So similarly, when all these are integrated, this is the result they will produce. Okay? Now, what was I trying to say here? Let's pay attention. So we have the following integrals. For exponential function, algebraic function is easy because we have done that like easily. Okay? For exponential function, integral of, let's say, exponential function. Please don't need to memorize. That's why I'm showing you this. Of course, nobody will ask you to show you what I'm showing you. To show what I'm showing you. So integral of exponential x dx from that third row or thereabouts is just going to be exponential x plus c. Okay? Now, I mentioned something on Zoom. Okay? I would like to say it again. If I have exponential ax plus b dx, that's another worksheet. Okay? So I'm just going to discuss everything together. If I have exponential ax plus b, we use something called integration by substitution. So we say let u be that ax plus b. In that case, du dx is going to be ordinary a. Is that not? Which means our dx times a is equal to du. Which means our dx is actually du divided by a. The reason is because the moment we write this as integral of u, to say dx doesn't make sense anymore. So this has to be changed to with respect to the variable with which we are integrating. That is why we need to do this. So we can substitute this in place of dx. And that will give du divided by a. So because a is a constant, it can leave the integral sign. And now you have the general rule, which gives you 1 over a exponential u plus c, right? Am I making sense? And that gives 1 over a exponential ax plus b plus c. So unlike differentiation, when you have a linear function, okay, you divide by the derivative. You don't multiply by the derivative. That's the point I'm trying to make here. So when I write result, I'm not going to go through this with all the functions. I'm just going to say times 1 over a or divided by a. Everybody should understand why now. Understand? So for this, the general form will be, if we have exponential, I'm not going to say f of x, because f of x could be any function, like quadratic, cubic, or whatever. Okay? So I'm just going to write it as integral of ax plus b, unless we had defined f of x to be x plus b from the beginning. So this is going to be 1 over a exponential ax plus b plus c. Okay? Similarly, if you have integral of a to power x dx. Bena, are you okay? Let's go here again. The derivative of this is this, right? So normally, I should have ln a by the side to be able to produce the original function, isn't it? So, we'll do this. How about ln a natural log dx? I've not changed anything, isn't it? So that one can go in and one can stay away. Can you see that? Then this will be my a raised to power x from the derivative formulas. So the integral of this will be 1 over a raised to power x plus c. So which is more or less a raised to power x divided by ln a plus c. Unlike in differentiation, when you differentiate, you multiply by ln a. When you integrate, you are dividing by ln a. Can you see a pattern here? Okay? And if you are dealing with ax plus b, after that, you still have to multiply by 1 over a. Am I making sense? So what I mean is, as a result of this, the integral of a raised to power, there's no ax plus b anymore. So let's say cx plus d dx. Are you with me? So while this is going to be the original function, cx plus d, you are supposed to divide by the natural log right? Then you have to also multiply by c. Then, oh, okay, I already have a c here, so how about we say kx plus d? Am I making sense? Then we have to multiply by k before we had c. Does that make sense? Now, that's that about exponential function. For trigonometric functions, we also discussed this, so this is like a review of what we talked about online on Saturday. For natural logarithm, the integral, so let's say this is 1, this is 2, this is 3. For natural logarithm, we know that this, from that second next step, is going to be the natural log of x plus c. Is that not? And from the generalization on the next step, in general, the integral of a derivative, actually absolute value of x, unless you specify x to be greater than 0, okay? This is the generalization on the next step, right? And this will give you the absolute value of that, natural log of the absolute value of that function. Okay? Now, if the logarithm is not to base e, let's look at the other one also. From the integral of that divided by that, oh sorry, yeah, okay, lane maybe a, for example, from here, I'm referring to that one. That gives me what? The logarithm, can you see? To base a of that function in general, provided this is not greater than 0 also. Are you with me? Okay? If you do not even think of it this way, you don't have to panic. You can actually do it from here. If your 1 over ln A is outside, and you have this, so this is even not relevant to be written, you can always simplify. This gives you natural log of f of x, isn't it? So that will be natural log of f of x divided by natural log of a. Can you see that? So let's write it clearly. Logarithm to base e f of x, logarithm to base e of a. Can't you write this as logarithm to base a of f of x by change of base? So that's why you don't even need to worry about this one. From here, you can always write the result of this one. So you don't even need to worry about this one. Okay? So I'm not going to worry about that. I don't think I should include that so we do not waste time and waste our memory space. Am I making sense? Quickly. So the next one will be, because the syllabus says the integral of the results you get in differentiation. That's why I'm going to do the results one by one. I'm sure some of them we can pick easily ourselves, but let's just go through it just for revision's sake. The next one is the trigonometric functions. That is a bit tricky, and we will still do more of trigonometric function, especially in integration by parts, integration by substitution. We'll do a lot of trigonometric function, but these are like defaults, okay? Default, like basis. The first one, the sine and the cos that we talked about already. Because the derivative of sine is cos, the integral of cos will be sine. Am I making sense? Now, because the derivative of cos is minus sine, the integral of minus sine should be plus cos, isn't it? Okay, I will say plus k first. I have a reason. So that when this minus comes out and go to the other side, I will have my integral of sine x, of course. Please, I need everyone's attention. To be minus cos, minus k, right? Then this, my minus k, could be the plus c. Am I making sense now? So this will be the integral of sine x dx minus cos x plus c. This we already talked about over the weekend. Okay, so you don't have to write it twice. I'm just trying to make sure all the results are following that. Now for tan, because the derivative of tan is sec squared, then the integral of sec squared will be tan. And all this linear function property follows for everything. So if it was to be sine ax plus b, after you write this result, you divide by a. We don't need to write that, isn't it? Okay, writing it once here is okay. Even here, we shouldn't have even bothered. Am I making sense? So I'm not going to write this function ax plus b for all of them. But now we see what happens when you have function ax plus b. Okay, so now for tan is sec squared, so the integral of sec squared dx will be tan x plus c. Okay? Similarly, because the derivative of sec is sec tan, so whenever you see that two products together, then you know that, oh, this must have been sec. Am I making sense? So 6, the integral of sec x tan x dx will give you sec x plus c. Ax plus b follows again. Provided you have the same ax plus b here, ax plus b here. You must have the same thing, otherwise, no. If this is theta, this must be theta. Yes, it follows. Okay? So I think we have two more. Cosec is negative cosec and tan and cot. So the integral, now that result is negative. So if your function is positive, what happens to your result? It's going to be negative. So the integral of cosec x cot x dx will be what together? Negative cosec, come on, x plus c. And the ax plus b factor follows again. Second to the last, for cot, you have cosec squared with a negative also. So what happens if you have positive cosec squared? What do you have? Negative cot x plus c. Okay? And then the special integrals. The integral of arc sine gives that square root. Arc sine and arc cos kind of look similar, isn't it? There's a question that asks you to integrate that, and you can get either of the result. Either you get arc sine or you get negative arc cos, both are correct. Okay? It's just some constant difference, multiples of something different. Anyway, so number 9, the integral of 1 over square root of 1 minus x squared dx, this is the result of arc sine. Am I making sense? So this will be arc sine of x plus c. Of course, if this has a squared, this is to be x over a. We talked about that in one of the assignments. I asked you to show that the arc sine of x over a is it's actually an impromptu test.
It was on the normal test.
It was on the main test?
Yes.
Aha. So it means if you have that general result, maybe we should write the general result. And I think there's a here.
Yes.
Right? Remember this?
Sure.
So this is going to be x over a. There's a way you can prove this. The normal way should be done in the exam. When we get to this point on integration by substitution, I will probably do one. I will ask you to do the other two. Okay? But the general result is in your formula booklet. No need to panic.
Mr. Daniel,
Yes,
on
sir.
top it's just 1.
No, for a?
Yeah.
Are you sure? Oh, so where did I get the a from? Oh, if I have a, then this would be 1 over a. Apologies. I think I was thinking of a different question. So similarly, 10. The integral of 1 minus now. Square root of a squared minus x squared dx. What would this be? Arc cos x over a plus c. And finally, the integral of 1 over a squared plus x squared dx gives what? arctan, yes, x over a plus c. All the results are written down so that when you are practicing, you can use them immediately. You don't have to memorize. I didn't memorize all of them. Sometimes I can mix one with two. But once I'm not sure, I already have the foundation. I know how it all began. I can always double check by scribbling something on my paper and I'm going to get it back. I don't have to memorize 25 formulas in calculus. And luckily we have a formula booklet, comprehensive as that, with all this. So the idea is not memorizing formula. That's one thing people fail to realize about mathematics. How you apply those ready-made formula is what matters. That's what makes you a good math student. Not how many, oh, we're going to give him a gold medal for remembering the area of a triangle. How does that help anybody? But you have a tricky question, then you can think, oh, there's a formula here, oh, there's a formula there. And that's the purpose of, some people think, oh, the purpose of this textbook is for me to just read all the time. When I was growing up, we used to envy people that read textbooks from back to back. Like they tell you, oh, I finished the textbook. And oh my God, such a genius. Reading the old textbook from front to back doesn't make you a genius. But can you apply the content of the book? Okay? Can you apply what it says? What are the things inside? Oh, if I see this question on differentiation, oh, is it implicit function? Is it parametric? Oh, this is the trick to apply. That's what makes you a good math student. I believe that is why IB provide a formula booklet. So they are not testing how much you can retain formula from your math classes, but how much you can apply those formulas from your math classes. Okay, so let's look at the second worksheet now. For the first worksheet, I said number 5 especially. I want us to look at number 5. Maybe we do that together because I believe, or maybe number 4. Have you been able to do number 4? Number 4 only requires expansion, right? So that's not a problem. Number 5. Have you been able to do 5a?
Yes.
Yes. So did you convert it into double angle?
Yes.
So 2 cos square minus 1 is just what?
Cos 2x.
Cos 2x, right? So with that, it is your ax plus b type of question. So when you integrate cos 2x, because the integral of cos is sine, it will be sine 2x over 2. That's the point. And what about the other one?
It's negative.
Negative what?
Negative cos 2x.
Negative cos 2x. Does everybody agree? Because your cos 2x in terms of sine should have been 1 minus 2 sine squared. But now you're having the other way around. So that must have been minus. So maybe we put that over there, especially because of our friends that are not here. So they are not part of this collaboration. So maybe I take this first. I'll send this to the WeChat group if anybody needs it immediately during the lesson. Otherwise, you can make use of it at home. Okay, let's go. Quickly, because of our time. Question 5, what? That's worksheet 1, right?
Yes.
So question 5b. Integral 2 sine squared x minus 1 dx. This is what we are talking about. We know that cos 2 theta is 2 cos squared theta minus 1. 1 minus 2 sine squared theta. What is the third one? Cos squared theta minus sine squared theta. Okay? So this is related to the middle one. However, it is placed wrongly, like in different directions. So for you to flip them, you have a negative. Then you're going to have 1 minus 2 sine squared x dx. This minus can't leave yet. Oh yeah, actually it can. This is now negative. All this becomes cos 2x. Now it's a linear function. If the angle is a linear function, you're good. If it is not linear, you have to convert it to linear. Okay? But if you have a square and there's a sine or cos, there's something we will do later. Integration of that by substitution. So this will be negative. Derivative of, now this is what you remember. Derivative of cos is minus sine. Integral of cos must be plus sine. Do you understand that?
Yes.
Okay? So this is plus sine 2x divided by 2 plus c. You don't need to take it back. Nobody cares. Just leave it this way. Okay? Let's look at, is it C or D? Which one looks technical again? C looks good. Or do we need to do it together? Yes, no? No?
I've done it.
You've done it?
I've done it.
Okay, C or D, pick one. Which one can we try together? C or D? Or none?
Which one do you think is harder?
I don't know. Until we start, I don't know which one looks. But I believe both of them are sweet. Sweet questions. Talk to me, guys. What? Okay, Miss Krista says C. Do we all agree?
Sure.
All right, so C. Question says integral of sine what? 2x minus all squared. So you expand the bracket. So I have sine squared 2x, right? The 2 will multiply, so you have minus 2 sine 2x cos 2x, right? Then you have plus cos squared 2x dx. Okay? These two can come together. Sine squared theta plus cos squared theta is what? 1. So this is sine squared 2x plus cos squared 2x. Of course, you can write 1 straight away. Minus 2 sine 2x cos 2x dx. The first 2 gives 1. What about this one? What is 2 sine theta cos theta? No. 2 sine theta cos theta gives what? Sine 2 theta. Sine 2 sine theta cos theta. This is the double angle for sine. Okay? This is the double angle for sine. So in that case, what would this be? Sine 4x. Hello? Can you see that? Because now your theta is 2x. Okay? So that's why this is sine 4x. So the whole idea is to make it linear. That sounds like linear. Okay? Make it linear. So this will be integral of 1. X. Integral of sine. Derivative of sine is cos. So integral of sine will be what? Negative cos. So that's negative cos. Then followed by? Over 4. Good. Plus c. So final result will be x plus, you can write 1 over 4 cos 4x plus c, or you can write divided by 4. So you have to remember this. And that will also be useful for the next question. Can I ask everybody to try 5D if you have not done it? Try 5D now. Two more minutes.